Hi, everyone. I'm Dr. Tanya Harrison, and I am a professional Martian who spent the last over a decade working in science and mission operations on different NASA Mars missions, including the Opportunity, Curiosity, and Perseverance rovers and the Mars Reconnaissance Orbiter. And today we're going to be talking about the Perseverance rover, which is the newest in NASA's giant fleet that has gone to Mars. So this is Perseverance, and its job is to look for signs of ancient life on Mars. And this is a key because we have to be careful of something called planetary protection rules. We don't want to contaminate any life that might be on Mars today. And so we're looking for places where there might have been life in the distant past that's probably not still alive today. And along with Perseverance, there was a little helicopter called Ingenuity that hitched a ride with it. And we'll talk about both of those in a little bit. But on Perseverance, it carried this little rover family portrait along with it. And this shows the whole evolution of NASA's fleet of Mars rovers over time, all the way from Sojourner through Perseverance and Ingenuity. And this has been not only an evolution in the technology that we've sent to Mars, but it's also an evolution in the science questions we've been trying to answer at Mars. So Sojourner was the first of these missions that we sent, and this was actually the first rover that successfully landed on any other planet in our solar system. And basically, the goal of Sojourner was to test, can we rove on another planet? Can we drive somewhere else? So this was a technology demonstration that was part of the larger Mars Pathfinder mission. The idea was to see, could you build something on the cheap? And it was about $280 million US at the time, which for space, even to this day, is still relatively inexpensive. As a comparison, the Viking mission was $1 billion. Curiosity and Perseverance are more like $2.5 billion. So $280 million rover, that's about the size of a shoebox or so, was pretty inexpensive. And we landed this at a place called Ares Vallis, which is the mouth of a giant outflow channel, so a place where we saw massive floods in the past. And it was able to confirm the former presence of water in the region, which we thought was there from satellite imagery. So this was the landing site for Sojourner, as viewed from the Pathfinder lander watching the rover drive around on the surface of Mars. And we could see that the rocks here were rounded, which we think means that they interacted with water at some point in the distant past. So we were able to confirm for the first time on the surface, yes, there had been water on Mars. So then we took the next step in 2004 with the twin rovers Spirit and Opportunity, or OPI for short. And the goal of those was to follow the water. And the idea here was, on Earth, anywhere there's water, there's generally something that has managed to survive there. So we sent the rovers to two places on opposite sides of the planet, one that we thought was a former crater lake for Spirit, and then one for OPI that we thought was an ancient playa, which is basically like a giant puddle that evaporates over time, leaves some salts and stuff behind, and then every once in a while the water comes back, but it never gets very deep. And in both of these places, we confirmed that there was both water at the surface and water underground. And in the case of Spirit, we actually found an ancient hydrothermal system. And that's really significant because we think life on Earth might have started at the hydrothermal vents near the bottom of the ocean. We picked where to land OPI based on thermal infrared measurements taken by the Mars Global Surveyor spacecraft, which operated from 1996 to 2006. And this map here shows the geologic composition of the surface of Mars in the thermal infrared. And if you don't recognize some of these words, they're basically all volcanic stuff, some dust, some ice, and this one bright red area in the middle, which is marked as hematite rich. And if we zoom in, that's actually this area here. It's the only place on the whole planet that looked like this, so obviously scientists were really intrigued. And it turned out when we landed, because we thought, well, if there's hematite here, this is one, interesting, since we don't see it anywhere else, and two, on Earth, hematite forms in places where water interacts with rocks that are really rich in iron. And so we thought we could find evidence of water with Opportunity. And it didn't take us very long to find that. These little blueberries, these little concretions of hematite that are literally the size of blueberries, are the source of this hematite signal, and we found them all over the place within the first 40 days of the mission. This is Sol 41, which means the 41st day of operations on the surface. So this told us that there was water here in the past. We didn't get quite so lucky at Jezreel Crater where we landed Spirit, which is this crater here at the bottom of a very long channel called Modern Vallis. And we thought that this meant this water had traveled through this valley, emptied into the crater, and formed a lake. So we were expecting to find lots of lake sediments left behind. But when we got there, all we found were volcanic things. And so that didn't necessarily mean it was never a lake. It just meant that any evidence of the lake had been buried by volcanic activity after the lake had dried up. And then the rover broke somewhat serendipitously. One of the wheels on Spirit actually stopped functioning properly, and so we had to drive the rover with the wheel dragging behind it, and it left this trench, and it exposed this bright white material, which is not something we had seen at the surface. And so the rover turned around, did some science, and figured out that this was made of opaline silica, which on Earth forms in hydrothermal environments like around volcanoes when that hot water interacts with certain types of rocks. And so we knew that there had been some kind of warm water in this area, which is a really good plus for finding evidence of life or life being able to survive the past. So then with Curiosity, we took the next step to signs for habitability. So we knew that there was water on Mars. We knew that it had been around for a while, but were the conditions both in the water and on Mars in general when the water was there something where life could have survived? So we sent Curiosity to a place called Jezreel Crater, which we also thought was a crater lake, sort of like Gusev. But here we knew that there was evidence of the lake at the surface because there was this 5.5 kilometer tall mountain of layered sediments sitting inside the crater. And the bottom half of these sediments have been carved by water as far as we can tell. So there's things like canyons and channels in it. And the top half of the mountain looks like it never interacted with water at all. And so we think that this mountain actually spans the difference between cold, dry Mars at the top and wet ancient Mars at the bottom. So Curiosity's goal was to land in this little ellipse here and drive up the mountain as far as it could and take samples of the layers along the way, analyze the different rock layers, and figure out what this lake was like and what happened as Mars dried up. And we have confirmed in the almost 10 years that Curiosity's been operating on the surface now that this lake did have all of the right conditions for life as we know it to survive. So now we're finally trying to answer the big question. With Perseverance, we are looking for signs of ancient life on Mars. And to do this, we went to yet another crater lake. So here's where Perseverance landed relative to all of the other missions that have successfully landed on Mars so far. This dark area here is actually a very large volcano called Syrtis Major. So we're on the flanks of that volcano here. So Jezreel Crater is an ancient paleo lake, so a former lake. And we were really interested in this lake in particular because it has valleys that come into the crater, but it also has a valley that goes out the other side of the crater. So we think that this lake was filled up by these valleys, the crater filled with water, and then eventually it spilled over the other side and just continued on its journey. So the fact that the crater had to fill up with water and then overflow tells us that the water was around for a geologically significant period of time. And we're most interested in this fan feature here. So if we zoom in on that, it's what we think is a river delta. And on Earth, deltas form when you have a river that empties into a standing body of water, like a gulf or a bay. One of the most prominent examples on Earth is actually this whole southern part of the state of Louisiana in the United States. That's actually the Mississippi River Delta, where the river is emptying into the Gulf of Mexico. So here we can see the little fan structure that is very characteristic of these deltas. And the delta is made up a lot of really interesting materials that we don't see in a ton of places on Mars. Things like these smectites, which is a type of clay, and carbonates. So this has carbon in it, which is really good for finding things like organics. So the goal is the rover landed somewhere about here, and it's driving toward the delta, and it's going to take samples of the layers in the delta and then cache them to send them back to Earth. So if you've seen any of the renderings of Curiosity in the past, you'll notice that Perseverance looks very similar. And indeed, the bodies are very similar. They've both got 6 wheels. They've both got this mast with a lot of instruments and a 7-foot-long robotic arm with a lot of instruments on board. They're both powered by nuclear batteries. But Perseverance has had a ton of equipment upgrades relative to Curiosity, and we'll go into some of those in a little bit more detail. So we've taken some pictures with the 23 camera systems that we have on board. And the cool thing here is that most of these camera systems are in color, whereas on Curiosity, a lot of the non-science instruments were actually black and white. So up here, this is an animation of some of the images that we took with our navigation cameras of dust blowing through Jezreel Crater. And you can actually see the tracks of Curiosity that's left behind. So it's turned around and looked back at where it was coming. These things way out here in the distance are actually the rim of Jezreel Crater. And then here, this is an image taken with the mast cameras, which is basically the science eyes of the rover. And then this is a close-up view taken with a camera called Watson. That's basically our microscopic imager. So these are all tiny grains of rock sitting on the face of a larger rock. And this can tell us a lot about what these rocks are made out of and the environment that it has experienced ever since it was formed. But one of the cool things with the camera systems that we were able to do with Perseverance is, oh shoot, it's not playing the video correctly. I can edit this part out. I'll just pause here for a second so you can cut and then go to the next slide. So one of the other instruments on board that's gotten an upgrade since Curiosity is the laser instrument that's actually in the mast of the rover here. And so on Curiosity, we had ChemCam. On Perseverance, we have SuperCam. And this is an instrument that basically blows up rocks with lasers, turns it into a plasma, and we analyze the light that comes out of the plasma to tell us what the rocks are made out of. We also have something called a Raman spectrometer that is really good at looking for organic material. An infrared spectrometer that can tell us what the rocks are made out of. And then a camera where you can actually take close-up views of the stuff that we've shot with the laser. And we'll see that on the next slide. And there's also a microphone on board, so we can hear what the surface of Mars sounds like in terms of the wind for the first time ever. These are some views from that close-up camera on SuperCam. And this is a hole that we've drilled using the rover. And we take profiles inside those holes so we can look at the composition of the rock as we go from the surface to the interior. And this is really important because that inside part of the rock hasn't been altered by interacting with Mars's atmosphere. And so it tells us a lot about how the rocks form. So each one of these holes is a place where we've blasted the laser maybe 5 to 10 times as you go down here so you can get this profile. Another thing that that Perseverance can do that is a huge upgrade over Curiosity is autonomous navigation. And so it can do this thanks to its upgraded navigational cameras, which take 3D stereo views, and then the rover can use that to make decisions over where it's safe to drive versus not. So here, the rover can drive a few meters, stop. It takes a panorama with the navigation cameras to figure out what slopes are safe for it to drive over. And then it will continue until it gets outside of the safe area that it has imaged with its navigation cameras. And then it will take another set of images to figure out the next part of its path. This is a huge time saver because before we would have to stop, take a panorama, send that panorama back to Earth. Human rover drivers would have to sit there and analyze everything around it to try and figure out what the safest path was. But we didn't always make the best decisions. The rover can tell a better job being there in person, so to speak, compared to a human. And so this is what that part of that drive actually looked like in person from the point of view of the rover. So that's Ingenuity there in the distance, the little helicopter. And here's the rover making some of its drive. And this was just back in July, so we're just now taking advantage of this opportunity. Another big upgrade that we got relative to being able to drive are the wheels. So on Curiosity, we had these wheels that were made out of thin aluminum, about the thickness of a pop can, and they were reinforced with these sort of wedge-shaped grousers. And there were a few holes in them that were actually Morse code that spelled out JPL as the rover drove along the surface, because we could use these as an odometry marker. These wheels, unfortunately, though, didn't hold up very well in the crunchy environment of the rocks in Jezreel Crater, and so they ended up getting a lot of holes punched in them. So these are the holes that are supposed to be there, and these are the holes that were not supposed to be there. The wheels are still completely functional, but we do have to keep an eye on them to make sure that these grousers themselves that are actually reinforcing the structure of the wheel aren't getting so damaged that will impact the rover's ability to drive. But we learned from this, and we made changes to the design of the wheels between Curiosity and Perseverance. So you'll notice on Perseverance, the grousers are much closer together. They don't have that sort of wedge triangle shape anymore. And we took out any odometry markers in Morse code, unfortunately, so no fun Easter egg there. But hopefully these wheels will hold up a little bit better. They're also made out of titanium instead of aluminum, so they should be much stronger in that regard as well. So these are the actual wheel on Mars doing a little bit of a wheel scuff, which we can use to look a little bit beneath the surface. And inside the wheel, we actually have another little Easter egg. So we've got the symbol for DNA here. and then something representing the tracks of the rover, looking sort of like unfolded DNA. There's also an instrument on board called MOXIE, or the Mars Oxygen In-Situ Resource Utilization Experiment. It's quite a mouthful. And this is an instrument that is about the size of a backpack, and it's generating oxygen on the surface of Mars. So here you can see it with some of the engineers for scale. This is a really important instrument because it is a test that is a precursor to sending humans to Mars, because we need to be able to generate oxygen for us to breathe. And so this instrument actually pulls in carbon dioxide from the Martian atmosphere, rips apart the carbon and the oxygen, and then creates oxygen that is breathable at the other end. And it does this through basically a solid oxygen electrolysis process. Sorry, solid oxide electrolysis process. So this is what that actually looks like. It pulls in the Martian atmosphere. It filters out anything that is not carbon dioxide, because there is a little bit of other stuff like water and argon and a tiny bit of nitrogen. And then it goes through this solid oxide electrolysis that electrochemically rips apart the molecules. And then you can actually get oxygen, carbon dioxide, and carbon monoxide out the other end. So this is good for breathable oxygen, and also oxygen for creating rocket fuel down the line, because obviously we have a lot of rockets that are powered by liquid oxygen here on Earth. And then we have our little helicopter friend, Ingenuity. So this is Ingenuity testing out its blades on the surface. And like I said, the rover brought Ingenuity with it, and it was actually mounted to the belly of the rover. So the helicopter was unfolded from the bottom, and then it had cables disconnected, almost like umbilical cords. And then the rover drove away, because if we were going to test fly this thing and it didn't work, we didn't want it to end up flying into the rover and causing damage. This is a selfie that Perseverance took of itself, taking a look at Ingenuity on the surface where it left it. And we take these selfies with a camera at the end of the robotic arm that actually turns around, points back at the rover, and then we'll take anywhere from 50 to 100 images that get stitched together. And when you do that, you sort of lose the view of the arm in the images. And so the goal with this instrument was to see if we could fly on Mars at all. We'd never flown on another planet. And so we weren't sure if the atmosphere on Mars was going to let us fly, because it's really, really thin. It's about the equivalent of being at 130,000 feet in altitude here on the Earth. But not only did it successfully fly, it has now flown 12 times successfully. This was the first test, which was just up and down, and we did progressively more and more complicated flights over time. So these are some views from flights 9 and 10 from the helicopter itself. So these are the black and white navigation camera views here and here. It also has a color camera on board, so this is one of our first aerial views of Mars from the helicopter, which is pretty cool. And we can see how the flight path on this particular flight was. The initial flights were just up and down, and then we flew a little bit side to side, came back, and then did some farther flights and came back. Here we actually did a one-way flight, so it didn't come back to where it took off from. So we're getting more and more bold with what we're doing since the helicopter has been so successful. The goal here eventually would be that you could do science with these that you couldn't do with the rovers, because you can get those aerial views. You could fly and look over ridges that might not be safe to drive on. You could also use it for autonomous navigation. So you're getting not only stereo views from the navigation cameras on the rover to help you, but these aerial views where the helicopter could fly ahead of the rover farther than you can see with the nav cams to get a better idea of plotting your navigation course. And then the biggest thing for Perseverance to answer that question about looking for signs of ancient life on Mars is the sample collection. And so this is actually a whole suite of instruments that is mostly composed of a drill and a caching system, where we're going through and we're taking drill cores that are a little bit thicker than a pencil, and then storing them in vacuum-sealed tubes that will then be left on Mars for a European fetch rover to come and pick up sometime within the next decade. Those samples will then be brought back to Earth to be analyzed in a lab, doing more complex experiments than we have the ability to do on a rover platform at this point. And so you might have seen in the news, if you're paying attention to these missions, that the first sample collection actually failed. There was something weird about the rock. But this is the first collection that we got just a few days ago that was our successful cache. And so you can see it actually inside the tube here. So what can we actually do with these samples? Why do we want to bring samples back from Mars at all? This isn't something that we've ever done before. The Chinese recently were able to collect samples from the moon and bring it back, but no one has ever collected anything from Mars to bring it back. And this way, we can sample a lot of different rocks from places where we know where they came from on the surface of Mars. So we have the geologic context. And we can use that to answer a lot of science questions. Namely, did Mars host life? That's obviously the big one. We can understand what prebiotic environments look like. So what do places look like where you don't have life, but maybe life could have formed? We can learn about how the rocky planets in the solar system formed in general. So Earth, Mars, Venus, and Mercury. We can learn about how the environment and Mars' climate has changed over time. We can look at how the magnetic field has changed over time because the Martian magnetic field has been a little bit of an enigma. We thought it had disappeared as the core of the planet solidified, but more recently we're finding evidence that there is some activity inside the planet and it does have a little bit of a magnetic field. And then we can use it to validate cratering chronology models for Mars. And this is something where we date how old a surface is based on the density and size of craters that we see at the surface. Right now, those are calibrated using samples from Apollo at the moon, but we don't necessarily know if that transfers directly to Mars. So this way we can get a better idea of how old the rocks are and how old the different surfaces we see on Mars are. So we don't have a ton of science results from Perseverance yet just because it landed so recently. It takes a long time to do instrument checkouts and make sure everything survived the trip to Mars, doing just fine. There's a lot of vibrations, there's vacuum, there's temperature extremes, so things can go wrong in transit. But over the next few months, hopefully now that we've done all the instrument checkouts, we'll start getting some good science out of the mission. And this mission is just building on top of all of the other ones to answer that big question of, was there ever life on Mars? We know from everything from Sojourner up through Curiosity and Perseverance that Mars had water and it had the chemical conditions that were good for life to thrive. We found things like organics, carbon, oxygen, nitrogen, all the key ingredients that you need for life to survive. So we know that Mars was habitable, but just because it was habitable doesn't ever mean that it was inhabited. So we have a big mystery here. Did we have two planets whose conditions were very similar at the same point in the history of the solar system, and life arose on both of them, but then life died on Mars because it turned into this inhospitable desert that we see today? Or perhaps the more interesting answer is Earth and Mars were very, very similar. They were habitable at the same point in history in the solar system, and Mars never got life, but Earth did. If that's the case, then it tells us that there's something really special about life and really special about Earth. There was an anomaly here that triggered life to form that didn't happen on Mars. And to me, that might be almost the more interesting answer if we don't actually find life on Mars, because it tells us that we're really special at the end of the day. And with that, if anybody has any questions about Mars or the missions or future plans for Mars, I'd be happy to take any of them.